Thank you. Thank you very much, Alexander. Thank you all for being here. I will share my screen now. I don't know if you are seeing my screen. Are you seeing my screen?
Yes, it's beginning. Yes, now it's okay.
Okay. So I want to thank the organizer, myself included. But uh, I apologize for using this hat. I'm waiting for my second shot, and my hair is so chaotic that I thought would be useful to use this hat. So I apologize for this. But I will talk about disconnect maximal torus and the topological entropy of powers. Uh, Even if you are not interested in topological entropy, I think maybe it will be interesting this talk, because I will try to emphasize the whole of structure theory of Lie groups in solving some dynamical system problems. So I will try to focus on the Lie theoretical aspects of this paper, and this is the structure of my presentation. I will try to give you the history and motivation of this problem, and then I will try to present. I'm going to try to present some details, but I will need to skip a lot of the details because I have no much time. So starting with the history, this is the history of um, entropy. Entropy is a concept developed in the end of 50s and in the until the beginning of 70s. First, Kolmogorov Sinai introduced the probabilistic notion of entropy. Then the topological entropy was introduced in 1965 for the compact case. And then in 1969, the relation between these two definitions was established, the so-called variational principle, which states that the topological entropy is the supremum of the probabilistic entropies when you take the supremum over all the probability, invariant probability measures. And in 1971, Bowen presented a formula for the entropy of the endomorphisms of connected Lie groups, but in fact, his formula is not the topological entropy of all the connected, but only the compact case, for the compact case. And something about 40 years later, I asked about the non-compact case. In the non-compact case, we still have a variational principle which relates the probabilistic and topological concepts of entropy. And first, I did this for proper maps, and after in 2016 with my students André Caldas, we did this for the general case, and we also looked for the entropy of endomorphisms in the non-compact case, and we find some results for nilpotent and semi-simple case. And recently, I present this result in our last school. We solved the problem for entropy of endomorphisms of the groups in the general case. In the non-compact, non-disconnected case, the general case. And I would like to stress here that for this paper, which was published in the Israel Journal of Mathematics, we use strongly the structural theory of Lie groups. And what I will present today is something which is also related to the structural theory of Lie groups. When we have a surjective endomorphism of the group, we proved that the entropy of the endomorphisms is exactly the entropy of its restriction to the maximum torus of the center of the group. So, and we have a very known formula for the entropy of endomorphisms of a torus. But this result, this relation here, implies that if G is compact with finite center, if G is compact and semi-simple, the implication of this formula is that because we don't have a torus, the torus is trivial, the maximal torus inside the center is trivial, the entropy is 0. So the motivation of this paper is to find examples of dynamical systems where the entropy is positive for all compact groups. I forget to say that for those who are not familiar with the concept of entropy, the concept of entropy is a concept of chaosity. When the entropy, the topological entropy of a system is positive, we have a very chaotic behavior of the dynamics. So I would like to have a formula which, for the compact groups, provide chaotic behavior for every compact. And so I consider the powers. When the group is abelian commutative, the powers are endomorphisms, and we can apply and obtain, for example, here, we can apply G to the square in C star. We have the maximal torus is S1, and we can show that the entropy is just log of 2, which is positive. And the question is, which is the entropy of G2 square in S3, for example, which is compact, semi-simple, has finite center. If psi was an endomorphism, then the entropy would vanish, okay, because of these results. And of course, it's not an endomorphism, and we will show that the topological entropy of powers will be always positive for compact groups. And we will establish a formula for the topological, an algebraic formula for the topological entropy of powers for every Lie group. So I will denote the map G to the power K by psi, and I would like to prove something like this. The entropy of a power is the entropy of a power restrict to the maximal torus of, instead of the maximal torus of the center, the maximal torus of the entire group. In the case of S3, this will lead to a positive entropy, okay, because the S3 has no torus in its center, but has S1 is a torus of S3, okay. So when K is compact and connected, this is very easy to prove, and I don't know why was not proved before. I've never solved this in a dynamical system book Maybe because people from dynamical systems are not always so used to the structural theory. Of course, there are a lot of people which have this background, but the most part of the dynamical system community is not very familiar with structure theory of Lie groups. And the center of my talk is this equality, which is very well known for the connected case. When we have a compact and connected Lie group, we have that the group is given by the union of its maximum torus. And if we define this map C here, which is the conjugation of the element T by the element G, we have by this formula that this map is surjective. And it's very easy to show that if we define a map capital psi is just is the identity in the first coordinate, but is the power of to the k power in the second coordinate. It's easy to prove that capital pi and psi are related. This diagram is commutative, and you get from here this equality. You can prove easily that the entropy of the power is the entropy of the power restrict to the maximal torus. Why? Because from the semi-conjugation, we have this first inequality is well known in dynamical system. The second one is directly from the simplicity of this map. In the first coordinate is just the identity, so it's not this first coordinate does not contribute to the topological entropy, and the second one is always true, so we get this equality, and the second equality is just the application of the formula to the torus. So this is very easy to prove, but my interest is to prove this in the general set. And for the non-connected case, for example, we don't have this equality. So I introduce what I'm calling the disconnected maximal torus, which is just the normalizer of a disconnected maximal torus is just the normalized of a maximal torus in K. So this is the definition, and it's easy to prove that the connected component of the identity is exactly the maximal torus, and we can also prove this. I will skip the details. The first part is this part here is very easy to prove. The second part is not so trivial, but we can use a result of Borel-Moskow from 1955 to show this. If someone likes I can present these details in the end, but we can prove this both of this, and so we can just repeat we can just repeat the argument for the connected case to the disconnected case. So we have also that the topological entropy of a power is just the topological entropy of a power, but now restricted to the disconnected torus. The second problem is to find that so this first equality is just followed by this decomposition, okay? But the second is what is the topological entropy when you restrict powers to a disconnected torus. And I will not present the details here, but but I can give you some hints in the end if you wish. It's interesting because you have to in the end the maximum entropy is in the connected component in T, and not the other components is not relevant to calculate. And to finish my presentation, I will just give you the hints on how we can prove the general result, how we can get a formula for the topological entropy of powers in a general Lie groups. First, we consider the union of maximal compact groups, and it's not difficult to prove that the recurrent set, this is the recurrent set of psi. The recurrent set is inside this union. The proof is not very difficult, but I will skip. And we can also use the following. If G over G0 is finite, I'm calling this the quasi-connect case. When we have a finite number of connected components, we can write X, the union of the maximal compact subgroups, in this way. And this is very easy to prove because we know that when G over G0 is finite, and this is in the NEB book, I used a lot NEB book in my first paper about topological entropy of endomorphism, and now I use also, and this is you can find in a book. But the second part is just an application of the result I proved in this paper. So and then from here is easy to get here. And with this, I prove in this paper this result, which is a general result from the dynamical system if we have a continuous map and the space is a separable. This result has nothing to do with Lie theory. FGs is a separable locally compact space, and the recurrent set is given by a union, nested union of invariant sets. We can prove this formula. The topological entropy of the total space is the limit of the entropy of the restriction to each of these nested subspaces, subsets. And of course, here we have exactly this, because these guys here, they are this union here is invariant by the power, because it's a union of subgroups, and we can apply just what I proved. This is true, and here, if we restrict the powers, here we can again apply that semi conjugation I used before, and we have this. So for this kind of group, we also have this formula, and the general case reduces to this quasi-connected case, because we can prove this. We can prove that, just a second, we can prove that the entropy of a power map in a general Lie group is the supremum of the topological entropy of its restriction to H, where H is quasi-connected. And so from this we get the result. So the general result is exactly that. The topological entropy of a power G to the k power is just the dimension of a maximum torus of the group times the logarithm of the exponent. So for compact Lie groups is always positive. And this is the end of my presentation. Thank you very much.
Thank you, Mauro. So, questions, remarks, comments? Mauro, I have one general question about the entropy. For example, we know that the topological entropy is a measure or can measure the behavior of the dynamical system, right? Then, for example, you said that if it's positive, then we have a chaotic behavior of the system, right? Now,
yes.
do you have some hope in using the entropy or topological entropy to study or classify the semigroup, for example, the semigroup of a semi-simple group like that?
Using entropy, I didn't understand.
Yes, using the theory of entropy.
I don't know, because I've never worked. I've never worked with entropy of semigroups. I think it's a little bit different for the traditional dynamical system definition. So I have no idea.
Yeah. Okay. Luisa Martin. Your microphone is closed.
Yes, of course. I have two questions. First, last time you were talking about this, I asked to relate the powers with the geodesic flow.
Yes.
This is
Yes.
the first question. Second question, maybe it's more on the direction of you are doing. My question is, how much these results can work for locally compact groups instead of Lie groups, where you can have also a good structure of compact subgroups. I don't know.
Yes, I don't know. The second question, I don't know. I've never thought about the general case when you have powers in a locally compact. But I think it's very interesting, because we know that when you quotient a locally compact group by a certain group, you get a Lie group, and maybe you can use this this way to get some information. But I think it's very interesting, because it's a much larger class of examples, and maybe people in even even in the compact case, because there are compact groups which are not the groups. Maybe it's still interesting. And about the geodesic flow, I thought about your question last time, but the point is that when you are looking to because you are iterating powers, and when you are iterating powers, if you look at the behavior of the geodesic flow on its base, which is the group itself, the time is doubling, is being multiplied. It's not the same. It's not the same dynamical system, even in the basis, because you are taking the power of the power, and it's appearing other thing. It's not do you realize it's not exactly the same? The time is going much faster in an exponential rate, and so I'm not sure if there is much relation between the topological entropy, because we know that in some situations the geodesic flow is in fact chaotic, but I don't know what is the relation between them. But one thing I would like to remark is, and I would like to ask a question to Neb, is that if do you, Neb, do you know this result about the decomposition of a disconnect compact group in this union of disconnected torus? Because I couldn't find, and I have to prove it. It's a simple result, but it's nice. It's not in your book, and so I'm asking you just to know.
Yeah, I think there is this notion of a Cartan subgroup of a compact Lie group.
Okay.
And this works well even if the group is not connected. Things become a little more complicated, but I think in the book by Bröcker and Tom Deek, there's a book, Springer Representations of Compact Lie Groups or so.
Okay.
They have this theory of Cartan subgroups, and I'm not so sure what the original reference is, but probably an old paper by Spiegel or something like that. So there is something of that sort.
Okay. But I would like to end just reinforcing that the list structure, the structure theory of groups was very helpful to solve a lot of these problems, and maybe there are a lot of other things that our communities can use to solve some dynamical system problems. This is my final remark.
Okay, more questions, comments? Questions. So let's start. Thank you to Mauro. Thank you, Mauro.